Ryland's lecture state. Okay, let's send this to projector. Let's try. No. That looks kind of good. See if that will advance or not. Okay, we'll mess with that later. Okay, Amin, are we good to go? Okay, thanks. So last time we were talking about, let's get a review of the very last slide we went over last lecture, because I was running out of time. So we were talking about what kind of cost of programmability is there in FPGAs, and we saw that it was large. Yeah, let's see here. So if we use we kind of use everything on the FPGA, the soft logic, the programmable routing, the hard blocks. The hard blocks like RAM and DSP you're going to see are a lot closer to ASIC density because the heart of them is essentially an ASIC. Then an FPGA is about 4x, the core of it, not including the IOs, is about 4x bigger than an ASIC that does exactly one thing with no programmability. It does the same thing that you programmed in the FPGA. If, on the other hand, you used only the programmable logic in the routing, that's where your gap is the biggest. We saw that the Rose and Quan paper said that that gap was about 35 times. I think that's a little high. What I saw when I was at Altera was more like 21x, so still a big number. The reason for the difference is they were using little circuits. So small circuits with like 1,000 lookup tables and so on. They were putting those in an FPGA that was designed for much bigger circuits, so it had enough programmable routing to route hundreds of thousands of lookup tables. But when they mapped it to an ASIC, they just went with whatever fit. And the ASIC tools would squish the cells very tightly together, and it would still route. They still had enough room for metal over it because it was a small circuit. If it was a larger ASIC circuit, usually you can't do that. Usually you become limited by the metal area, not by the standard cell area. It's not an enormous phenomenon, so that is why my belief, based on some studies and things that I saw when I was at Altera, is that this 35x is a bit too high because it's based on these small designs. And if you used larger designs in an ASIC, even if they were all logic and wire, they'd be more in the 20 range, which is still a big number. Okay. Again, if hard blocks, use a lot of hard blocks though, you're down at 4x. So still a pretty big range. Speed wasn't affected very much by whether you used hard blocks or not because you're limited by the slowest part of your design. It tends to have a lot of programmable routing on it. So whether you have hard blocks or not, speed is typically around 3x slower than an ASIC. So as I said at the end of last lecture, area delay is an important figure of merit. If you're trying to figure out how much processing can I get in a unit of silicon, because I could clock it faster if my delay is lower, or I can put more copies in if my area is smaller. So area delay is the inverse of both those things. It's like the inverse of throughput I can get if I have a lot of parallelism. So the area delay product's pretty big, right? 12x if we are using lots of hard blocks, that's our best case, and 60x if we're using almost just all the soft logic, not really any of the hard blocks. This lines up reasonably well with a more recent study that was done by Andrew Boutros, one of my PhD students, where he looked at deep learning accelerators, so much bigger designs. These are now hundreds of thousands of lookup tables, and they're doing something fairly interesting and complicated. They're accelerating convolutional neural networks. And he did that in an FPGA for several different accelerators. And then he took the exact same design and he mapped it to an ASIC. All right, and he looked at how much smaller did it get. And each of these designs used a mix of RAM and multipliers or DSP blocks and logic and so on. The area gap was still pretty big, about 8x, and the speed gap was big, about 4x. But he's kind of in this range that we said you should be in, okay? Now this, this might look like a pretty strong case of, well, then put it all in an ASIC. It's important to realize that the ASICs he designed are not something you would ever make and sell because these ASICs would accelerate exactly one neural network, which is not a big enough market to make any sense for you to make an ASIC. Whereas the FPGA, he could reprogram to do other stuff, put more things in it, et cetera. So this is kind of like a limit study. Like if you had such an enormous market and you were convinced this neural network is going to stand forever and you got everything right, that's the gap you get. But in practice, those things aren't really true. You're going to have to put some programmability back in the ASIC, which is going to narrow this sum. Okay, so then the last thing we talked about is process technology. Process technology matters a lot. So if I made one of these ASICs, first I'm not really going to make it. I'm going to put programmability back in, so I'm going to lose some of this gap. And I'm probably not going to do it in the same process technology as the FPGA that I can go buy, because that's very expensive. So how big an impact is that? Well, as I said at the end of last lecture, the average ASIC start is 3 process generations behind the state-of-the-art FPGA. That's where the bulk of ASIC starts are. They're usually 3 generations behind, and that's a big gap. So in area, that's an 8x density loss, and in speed, it's 1.5, maybe 2x speed loss. So it narrows this gap a lot. But definitely there is a gap, no matter how you slice it. Yeah, go ahead.
I just want to check the term, like the area delay. So does that mean the delay per unit area?
Delay is just delay of your circuit, okay? The reason that we care a lot about area delay is essentially the inverse of throughput, if you have a lot of parallelism, because you can clock your circuit faster to get more throughput, or you can make more copies. If I have a smaller area, if I have half the area, I can make twice as many copies. If I have half the delay, I can clock twice as fast. If I have both those things, I can have 4 times the throughput. Does that make sense? That means the throughput is exactly proportional to 1 over area delay. So often when we're trying to figure out how good is some compute device or some silicon process, we talk about area delay because it combines those things together. Does it make sense? But it's bad. Throughput is good. You want area delay small, therefore 1 over it is big. Does that make sense? And yeah, area delay is not some normalized thing. It's delay of like some standard critical path. So like the critical path in your design.
Another question is that even with the generation delay, because the ASIC is always 3 generations.
It's not always 3 generations behind. So I mean, if you have a market that, if you've got investors who have $1 billion and you've got a market of 10 billion, go hire an engineering team of like 200 people and go for the latest ASIC technology. But that's not the typical opportunity.
I mean, even the ASIC is 3 generations behind, but they still have a that.
Well, so you have to take this number, 12x area delay, roughly, and now you compare it to, for example, the kind of numbers that we were getting for the FPGA programmability cost, and it's in the ballpark. Okay, if you're using the hard blocks a lot, then this means you're around comparable in terms of efficiency. If you're using all the programmable logic, then you're probably still behind. Does that make sense? But the FPGA also still doesn't this ASIC's still not free, right? 3 process generations behind makes it significantly more affordable, but that means instead of spending $100 million to develop it or $200 million to develop it, maybe it'll only cost you 30 or 40. That's still a lot, right? So you better not have like a small market. It just doesn't have to be quite so big. Does that make sense? Okay, so who read this paper? This paper was one of the ones that was assigned last week. How many people managed to read it? This gives me okay, we got at least 1, 2, 3, 4. Okay, so I like this paper. What did other people think of it? Maybe I've now biased you. Any thoughts? You go like, I wish I hadn't read that paper. I read it, but I refused to submit a questionnaire because I want to force myself to read a different one. Or you had, that was pretty good. I liked it. What do you think? Did you like it? Okay, so good. Why did you like it?
I like the fact it was new to me that a paper dived so deep into like each individual application, like good set of different various applications which require a bigger throughput, and they tried to fine tune those applications to the strengths of the CPU versus the GPU, and then compare them, making it a very comprehensive, fair comparison.
Yeah, that's a great answer. So I think they did a good job of diving deeply into the set of applications they looked at and really trying to get the most out of the CPU and out of the hardware. So I'm not going to go through all the details of this paper, but one of the key things that comes out of it that I found really interesting is what this paper does is they take several compute kernels, so like little programs that are doing important but somewhat repetitive calculations. So they're not taking like a program with 100,000 lines of like random code. They're taking kernels that have, maybe a few hundred lines of code, but are doing, things like convolution or correlation, things that happen a lot in larger programs and are compute intensive. And they're checking how fast do these run on various types of processors versus what if they just built the exact hardware they need. These kernels, they're doing relatively repetitive operations. They can put them right in hardware and just directly execute the computation. They have loops in them, so the hardware can't do it all in one clock cycle, but they can have the hardware over many clock cycles with a high degree of parallelism go and compute what answer the program would get. And they do this for a set of, I think I have them on the next slide, but a set of 6 or 8 different applications. And they compare, just from an efficiency point of view, how efficient they're basically building soft processors. So they're building the processor on the FPGA versus building the hardware on the FPGA. So basically both have the penalty of the fact that the FPGA is programmable. That's common to both. So what they're trying to get is, what is the efficiency of the 2 different programming models, okay? Not the efficiency of an FPGA versus anything else, just what's the efficiency of hardware doing exactly what you want versus a processor that's interpreting an instruction stream and gradually building up the computation you want. And the gap is very large, okay? We take it for granted that we use processors for all sorts of things, so it's interesting how big the gap is versus hardware that just does one thing. So they found that over this suite of benchmarks, when they average it, that a scalar processor, so a scalar processor again is who remembers what a scalar processor is? Or maybe I haven't even used that term. Do you know what a scalar processor is? Any idea? Yeah, what do you think? It means one core, sure. So it is one core. Scalar means something else though, but you're right, this is a single core. So I guess scalar can only be defined as it's not vector in a way, okay? So that's kind of the meaning of scalar, just means not vector. So it means it doesn't have SIMD. It's like in your first computer architecture class where you built a processor or looked at a processor, it's like, one instruction adds 2 numbers. That's this processor, okay? Classic processor. And it's a lot bigger and a lot slower. Mostly it's not slower because of cycle time, like frequency. It's because it needs many cycles to compute the same result as hardware does. So it's 432 times slower and 6.7 times larger than just building a hardware circuit that does exactly what you need for some kernel. So if I multiply those together, I get a huge area delay product, so a huge drop in throughput. And I'm going to get about 1/2900th the throughput from this scalar processor. Now, they didn't just stop at that, so they can build a bunch of different processors in an FPGA. So they built vector processors, and they built them with different, so these are, again, SIMD processors. So one instruction doesn't just add 2 numbers, it adds maybe 8 numbers, 8 pairs. So they built vector processors, and they experimented with, well, what's the best vector width, so how much SIMD? And they found the best one was 25 times slower and 36 times larger. So why do you think it got larger? Does it make sense that the vector processor got bigger? What do you think? Yeah, it makes sense. It has many functional units. Okay, so it's still one core, like one instruction stream, but it has, instead of an instruction saying, add these 2 numbers, which takes 1 ALU, it says add 8 pairs of numbers, which take 8 LUUs. So it makes sense, it got bigger. But it got fast, it increased its performance by reducing cycle count by more. Okay, so it's a net gain. So 25 times slower now than hardware, 36 times bigger, so 900x area delay product. And that best one was 8-way SIMD. So they could make the programs run faster if they went to 16-way SIMD, but the area starts getting quite big, didn't quite pay for itself. So that was kind of the sweet spot. Yeah?
So since we already know that it is 25 times lower,
Yeah.
what's the point to, like, we also get the 900 times average delay, like, are they?
So you're saying, why would you do this?
Yeah, because I think the slower, like.
So on an FPGA, you probably shouldn't do it, right? They were basically investigating the efficiency of programming models. So this says if you can actually just build hardware, for example, streaming hardware, which is a pretty powerful, efficient form of hardware, that was the basic style they were building. If you can build that for your computation, it is a lot more efficient than a processor. So on an FPGA, if you can do this, then you should be building the hardware for these applications. The soft processor was very inefficient. Does that make sense? Unless it was a computation that wasn't very important. If it wasn't very important, then most of your system is elsewhere, then maybe the soft processor is good enough. But that wasn't their point. They basically were just trying to figure out how efficient is a processor versus directly executing in hardware. And it varied a lot depending on, I guess one thing, I have some caveats on the next slide. It wasn't the same for all applications, right? So it's not like it's one number. This is a blended average, but there are different, quite significantly different numbers depending on what you're doing. Okay, we'll talk about that in another couple slides. Okay, so what does this mean? And this is based on feedback from prior students. This may be the most confusing table that I show you. Okay, I've tried to refine it, make it less confusing, but you're going to tell me whether I succeed or if this just completely baffles everybody. I'm going to check with Amin whether it baffles him too. So, okay, so this is my attempt to kind of put together various forms of programmability and programming models. So let's say that I have 100% confidence that I'm building exactly the right system with no changes, no differences between customers, and I'm going to get it exactly right. And I have an unlimited budget to do it. I build an ASIC, and my ASIC is like all streaming hardware and other types of hardware. There's no instructions, no programmability, nothing, okay? I'm going to define its area to be 1, its delay to be 1, and that means its area delay is 1. Okay, that is the most efficient system I could build. It's also the most expensive one I could, like, from a non-recurring engineering cost. It's the most expensive one, and it's the most risky, right? So now let's say I don't have an infinite budget. So I say I'm going to build the same thing. I'm going to build hardware, but I'm not going to make an ASIC. I'm going to put it in an FPGA. And that gives me some flexibility. Like I can actually change this if I have different customers or I get some things wrong or there are bugs, et cetera. So, but we just saw that the area is 4x to 21x bigger. 4x if I use the hard blocks a lot, 21x if I don't. Delay is about 3 times bigger, so the area delay is this pretty big range, 12x to 60x. So it's a lot less efficient than that ASIC. I could also just go and buy a scalar processor. So I'm not going to make a soft processor in the FPGA. That's like too much programmability. I don't want to lose that much efficiency, and it doesn't really make sense to me. But I can just go buy like a relatively simple processor that does one set of data at a time. And if I do that, my area from the previous paper we just looked at is 6.7x bigger. My delay is 432 times bigger. My throughput's down by 2900x. But it's more common nowadays. If you care about throughput, you're probably not going to buy a scalar processor. That nowadays tends to be a relatively low-end microcontroller. Every high-performance processor you can buy has SIMD instructions. And GPUs also have SIMD instructions. They're like a form of vector processor. So I would probably buy a vector processor instead, and it's not hard. That would be 25 times more area and 36 times more delay for 1/900th the 1/900th the throughput. Okay, so of these things, basically all 3 of these have some form of programmability. Okay, the first one doesn't, so it's too risky for most people. No programmability, huge non-recurring engineering charges. So if I look at these ones, the most compelling are this. I use the FPGA and I take a big efficiency hit versus ASIC custom hardware, or I go buy the vector processor. If I compare these two, the FPGA actually looks pretty good. Okay, the FPGA is actually somewhat smaller. Let's see. How did I get 6x? I don't know how I got the 6x, but you get the idea. So it's somewhat smaller, significantly faster than the vector processor. So it actually, in area delay, comes out ahead. Does that make sense? So what this says is FPGA programmability has a big hardware cost. It's not small. But it enables you to use a much more efficient programming model. You can actually get rid of instructions and just directly execute in hardware. Or you can make very complicated data paths that still have some software control, but not much. You know, your data path is kind of huge compared to the instructions that are controlling it. The net result of that is that it usually wins versus a processor if there's enough parallelism. Processors are also programmable, but in a different way. And they also pay a large penalty for that programmability. So does that make sense? Did I confuse people with this table, or do you kind of get it? Yeah. It is programmable by an instruction stream. Okay, so its hardware is not reprogrammable. It's all gates and so on. Like you can't say, I bought a processor that's 8-way SIMD with these instructions and I don't like them anymore. I want to make some new instructions, or I want to change it to 16-way. You can't do that, right? You bought the processor, that's it. But it is programmable because it has an instruction stream. Does that make sense? No, so it wouldn't be a soft processor in this case, because I'm saying you're using a very efficient programming model. So say streaming hardware, where you've got a pipeline that just does exactly what you want. That's what gets you to essentially pretty efficient FPGA numbers. If I build a soft processor on the FPGA, I essentially am stacking the FPGA programmability cost, which we just saw in area delay is something like 12 to 60x, with the processor programmability cost, which we saw is actually several hundred. So that's why I say that if you're going to build a soft processor in an FPGA, you've got to be careful what you're doing. If it's just housekeeping, that's fine, because it's just not that big, not that important. That's one way to go. The other way to go is it's a weird processor. Like it's got a lot of really specialized hardware. Because if you're just building, a very vanilla soft processor, and then you're saying do most of my compute and do it on an FPGA, it's not great, right? Like that 2 levels of programmability is kind of a killer if you want to do a lot of compute. Does that make sense? So you get programmability in 2 very different ways here. There is a big results. So one thing I don't want you to go away with is take these as I'm walking through some kind of important papers that try to quantify these, but they all have big results, and they are. Don't walk away saying, I just figured out that an FPGA is always at least 9 times more efficient than a vector processor, because that would not be a valid conclusion. And I'll get in trouble when you find that's wrong in your work, because it's going to be wrong for some things. Was there a question? Yeah.
So on the table, so it says ASIC and scalar processor. Does that mean
Okay, I think it's sorry, my computer's trying to answer your question. I think that was Cortana coming up going, I know the answer to this one. I would like to see if Microsoft is actually able to answer that question. That would be awesome. Sorry, say that again?
Yeah, so on the table it says ASIC and the processor, the scalar processor, vector processor. Does that mean we integrate them together on a single?
Well, you could put a vector processor. They do actually do this. Like when you buy a lot of high-end FPGAs now, they actually have a hard vector processor, usually ARM, included on it. So you actually get some of each. So you can do that, but you don't have to. You could also just go buy a Xeon, right? Like go buy an x86 high-end processor and say that's what I'm going to run on. Or go buy a GPU.
Yeah, I'm curious how the paper see.
So the paper that I just went over basically did everything soft. So they did a bunch of different soft processors versus hardware implemented in an FPGA. So everything was on an FPGA, and that was on purpose. They're trying to figure out how efficient the programming models are. They're not, otherwise that study makes sense to do either everything's implemented on an FPGA, so all you're changing is the programming model, or everything's implemented on an ASIC, so all you're changing is the programming model. The everything is implemented in an ASIC is a lot more expensive and slow and hard to do, because they would have had to fabricate about, 20 or 30 chips. Doing it all on an FPGA is a lot easier. Does that make sense? But they were just trying to answer questions about programming model. They were not trying to say whether you should then build it on an FPGA or an ASIC. Okay, so a few caveats. I guess I kind of already addressed this, since it seems most people didn't read the paper. Maybe I'll just talk about them. The operand sizes in their benchmarks were, they had a Viterbi decoder, I think, was the one that was 1 bit. Then they had an 8-bit benchmark, 2 that were 16, and 2 that were 32 bits. They were all integers. So those are their benchmarks. Do you think this had an impact on their results? So this is the paper trying to compare the efficiency of various processors to direct hardware execution. Does it matter? Does it matter what the precision of the operands are in the benchmarks? So like the data type, whether it's 1-bit data or 32-bit data, doesn't matter. What do you think? Do you think it matters?
It matters. Of course, we have a floating point algorithms.
Yeah, so you're saying it matters, and yeah, it does matter. Okay, so a processor is optimized for typically 32-bit integer, maybe 64-bit integer even, and also the floating point units. It's not really optimized for 1-bit operations. It can do them, but in hardware, if I have 1-bit operations, I just build the data paths 1-bit wide. It's super efficient. Processor, I don't get to, even if I'm only using 1 bit of my 32-bit wide data path, I don't get to remove the cost of the other 31 bits. So this is kind of an ideal case for an FPGA. 1-bit wide data and a high data rate. 8 bits is pretty favorable to an FPGA. 16, kind of in the middle. 32-bit integer is pretty efficient on a processor, so that's actually somewhat processor friendly. Floating point is even more processor friendly because you have hard floating point units on processors and even more on GPUs. So as you get to these larger data types, it would affect the gains, right? You're going to get the biggest gains from hardware execution here, the smallest gains up here. Okay. I guess I already talked about this. So they gave a comparison of both a scalar and a vector processor. The processor is the more relevant one because if you've got a lot of work to do, you're going to use the SIMD instructions in an Intel or ARM or AMD processor, or you're going to use a GPU, which is another form of SIMD or vector. Okay, so that's finishing off that programming model discussion. Any questions on that? Okay, if not, I'm going to go on to the kind of main topic of today. Okay, so assignment 2 I haven't released yet, but I'm going to release it. Should be out tonight. It's due Monday, November 1st at 11:59 p.m. Or I might make it the 2nd. I don't know. People sometimes want one more day, so if I get it out late tonight, I'll kind of feel bad and I'll make it the 2nd. You're going to be optimizing. So it's a lot like assignment 1, but you're going to be optimizing a more complicated computation. So it's two-dimensional convolution, where there are a few more things that you can play with. I'll give you a prize for the highest throughput. So you get fame. I'll announce who you are in the class, and you'll get an Amazon gift card. So you pay thousands and thousands of dollars in tuition, but you have the chance to win a small gift card. So perhaps teaches you gambling doesn't pay, but pleasure is in the journey, not in the reward. You're also going to compare to, so you're going to basically optimize this computation on an FPGA to see how much throughput you can get. We're trying to make a high throughput system. You can make a high throughput system by making it take fewer clocks, making it run at a higher frequency, being smaller so you can fit more copies in. Combine all of those, and you get the best answer. You're also going to compare to a CPU and GPU implementation. So we're not making you write those because this isn't a CPU coding or GPU coding course. You're just going to basically look at them, compile them, run them, so that you can make some comments about, okay, how do these devices compare? Because that's one of the things we've been talking about. And you'll compare them in throughput, throughput per watt, and throughput per square millimeter. And the assignment handout gives you enough information to do that about what's in the UG machines and what are the die sizes and all these things, so you can do this comparison. Okay, so you're doing two-dimensional convolution. Okay, who remembers convolution from back in Signals and Systems in probably second year? Somebody must remember convolution. There's got to be somebody who's still working on convolution. No one remembers convolution? Is this for real, or are you just like kind of, you're just pranking me? You're like, we're just going to make them think. Next lecture, we're going to make them think we forgot how to add, right? Like we all make a deal on Facebook that nobody's answering a question about addition. So, what do you think? You remember it?
Multiplication in the time domain is the
Yeah, so convolution has this really nice property that multiplication in the time domain is the same as convolution in the frequency domain, and vice versa. So convolution in the time domain corresponds to multiplication in the frequency domain. So we use it a lot in signal processing. We want to like pass something through a certain filter. If we convolve the signal in the time domain with some filter, it's equivalent to like multiplying its spectrum with, just the characteristics in the frequency domain of, say, a low-pass filter. So that's what we're doing here. So this is one-dimensional convolution. So it's like a sliding window computation. You take incoming data. So for 1D convolution, this might be sound, for example, or it might be signals from an antenna for radio. We store a bunch of signals so that we have some window of signals available, and we multiply them, each signal, by a certain coefficient in our convolution, and that we add them all up. That gives us one output. Then we slide all of our data in our window over by one, add in one new data point, and repeat. So these are the filter coefficients for a low-pass filter. If you remember from signals and systems, this would be a continuous time filter. We are implementing this in discrete time, which means we just have dots at certain, we have coefficients at discrete points in space, and we have samples at discrete points in time. And a finite impulse response filter implements this computation. So our output, y, is basically just our last n inputs, x, each of them multiplied by the appropriate filter coefficient. And if we chose the filter coefficients to look like this function, this would implement a low-pass filter. What comes out will not vary nearly as fast as the input. Don't worry, this is like background. You're not going to be tested on signals and systems or have to like devise filters. Is everybody with me so far? That's 1D convolution. Okay, but we can do convolution in more dimensions than 1D. So in signals and systems, you probably use convolution I'm guessing almost exclusively in 1D. When I was an undergrad, we did. But you can do it in higher dimensions too. So you're going to do two-dimensional convolution in this assignment. So you're given a test bench, well, several test benches that have, some little images, some bigger images. Your performance is measured on a bigger image. I think it's 512 by 500. And you're applying a 3x3 filter. So you're basically have filter coefficients, 9 filter coefficients. You're going to take 9 values in the image, multiply them by those filter coefficients, and you get one output. Okay, so once I have these 9 values in, multiplying by the appropriate values, add it all up, I get one output. And then if I want to get the next one, I have to shift over my window, look at these 9 values, and that'll compute this next one. When you're doing this in hardware, it's convenient to pad the image. Okay, so we are padding them with zeros. The reason for that is your hardware can kind of do the same thing all the time. You don't need a lot of special cases that would lead to muxing and complexity in your logic. So these zeros aren't really in the image. We're sticking them around the image in our hardware so that we can always apply this 3x3 filter and get a value even at the edges. Does that make sense? Okay, we're going to send the data into you. If you look at how the test bench works, the data is going to be sent in 1 pixel at a time. Well, sorry, I shouldn't send in those. But the data is going to be sent in 1 pixel at a time. And once you have 3 rows, well, you have the padding plus 3 rows, or basically the green values here. Once that much data has been shifted in, you have enough input that you can compute this first pixel. Now when another value comes in, you have enough data to compute the next one. Another value comes in, you can compute the next one, and so on. And then once the last piece of data arrives down here, you can compute this last output pixel. Okay, so you have a simple input protocol of data is going to come in 1 pixel at a time. You have to decide, okay, how are you going to buffer this? So write some HDL to put this in some buffers so you have the data that you need to feed into some kind of multiply accumulate engine that you're going to write to do the convolution and then write the data out. Does that make sense? Okay, and you're gonna have to keep track of, as you go from one row to the next and you get a couple of these padding pixels, you aren't gonna be able to generate any valid data, so you don't wanna send out a value then, right? So you have a little control logic to say no output right now. Okay, so the interface looks a lot like it did in Lab 1. So you've got 8-bit data coming in, and you're told whether or not the data is valid in any given clock cycle. So you can't assume that every cycle there's valid data. Maybe sometimes the upstream logic is not ready to give you something. You're going to build hardware that buffers the data, does the convolutions, and then outputs them in row major order. So row major order means like this. Go across like that, then down, across like that, and so on. Because that's what the test bench expects. Whenever you have a valid output, you bring O valid cycle to say I got a valid output, and you output it. So if some cycle, if it takes you several cycles to compute an output, then you don't raise O valid. And the test bench won't read until you say I've got a valid output. Yeah?
So we don't need the back pressure like the ready.
We do actually have a ready in here. I think I just didn't write it on here. Okay? So there is actually back pressure that you should also handle. And yeah, probably should put that on the slide. Okay? So there is an I ready coming in here. And there is an O ready coming out here. And you should set those as well. Okay? Whoops. Okay, it was there. I thought I had it. Okay. I should have just hit click. I animated it. My animation was too clever for me. The other input you have are the coefficients. So there's a 3x3 filter. So there are 9 8-bit values. We won't change those. Okay? So those are just, you can embed them in your hardware, put them in registers. We won't stream them in. Okay? At least we won't change them, based on these inputs. Okay, so a few tips on this. So you can write everything in basic Verilog. But if you write everything in basic Verilog, you're relying on Quartus inferring what do I mean by this. So for registers and for logic, that works fine. Multiplexers, gates, basic RAMs, it works fine. For basic multipliers, it works fine too. You can just write times and so on. But more complicated hard block features, Quartus usually will not infer, meaning it won't infer your HDL and say, oh, you want to use a DSP block as a multiplier plus an accumulator with registers on its inputs and outputs. It usually is not going to figure that out. I think probably it never figures that out, but in case some clever CAD engineer has made it better, I'll just say usually hasn't. So if you want to use those more complicated features of a hard block, like particularly the DSP block. In this assignment, if you use the DSP block well, you can get better performance. In Quartus, you go to Tools IP Catalog, and you'll see a display like this. You'll see a whole bunch of different IP. So these are hardware libraries, right? So pre-built functionality that you can use. So the 2 blocks of IP that are going to be pretty useful to you are this DSP, primitive DSP, native fixed point, Intel ARIA 10, FPGA IP. So basically, if you go into that block, it'll instantiate a DSP block and give you full control over it. So I wouldn't do this at the start. This is not like the first thing you do. But if you want to, once you have a system working and reasonably optimized, you can say, I want to control everything about the DSP blocks, hook them up in what I think is the best possible way. This lets you do that, okay? But again, get simple things working first, because trying to do, most of development is actually debugging. If you try to change too many things at once, your debugging is really hard. So it's not a good idea. Get something simple working, measure it, then change 1 or 2 things, trying to make it better, test and measure it again. The other functions you're going to find probably quite useful are the on-chip memory functions. Okay, 2 of the IP cores in here that might be useful to you are the 2-port RAM. Okay, so 2-port RAM lets you do a read and a write at the same time. And the block RAMs on the FPGA are very efficient at that. They're built to do that. and that's quite useful in this kind of computation where you've got data coming in and data going out at the same time. Another one that can be useful is the FIFO IP core, which is similar, right? A FIFO has data coming in and data going out. It's just basically the next item of data goes in the first free spot, and when you take data out, it comes from wherever the oldest data was. So it's kind of similar to a two-port RAM, but a two-port RAM gives you a little more flexibility. You specify what are the read, where do I want to read from and where do I want to write to, whereas in the FIFO, it's all done kind of automatically. It figures out where the read and write should happen. And this FIFO mega function, or IP core, will be behind the scenes. It'll be built out of RAM or shift registers based on whatever's more efficient. So we talked a few lectures ago about how usually RAM's more efficient, but for small ones, shift registers might be. This IP core knows that. It'll choose what's more efficient automatically. So using these IP cores can save you quite a bit of effort, and can also have higher performance than what you would probably wind up writing yourself. Does that make sense? Okay, so all right, this is just a reminder of, so you're doing two-dimensional convolution. A neural network, I think, would be like a bit too much to do in an assignment, but convolution is the key building block. Two-dimensional convolution is the key building block of convolutional neural networks. So who's heard of a convolutional neural network? Interesting. So more people have heard of that than heard of convolution. So I think I caught you. Yeah, so most of you are aware of that. This is like a classic one called AlexNet. But basically, most of the computation, like up in the high 90s, is basically convolutions walking through feature maps. And the feature maps start out as pixels, and then they become the output of whatever the previous layer generated, which is harder to say what it is, but you can interpret it as like generated pixels. And a hardware accelerator basically walks through all of these tensors, these blocks of feature data, applying basically two-dimensional convolutions all over and over and over again, sometimes adding them together, and then writing them to the next layer. You do that for several different layers, and then there's a final fully connected layer, which basically means multiply accumulate units that just multiply all this data by some weight and produce an output. You go through one or a couple of those fully connected layers and you produce an output. So this particular CNN is an image classifier. So its final output is, its input is pixels, just like what you're taking in lab 2. And its output in this case would be a vector of values that correspond to the probability that it's different classes, car, truck, van, etc. And there's actually just a nice animation of what that is. So this is an animation of those convolutions. So you can see it's just sliding over, multiplying a whole bunch of data, adding it up, writing out the outputs. So that's kind of a classic, what the CNN community calls a 3D convolution, even though it's not actually a 3D convolution. It's actually a whole bunch of 2D convolutions. And that sometimes they also have other layers called depth-wise and point-wise convolutions. But the depth-wise one is, again, based on a 2D convolution, and the point-wise is based on a 1D convolution. So the building block of all these CNNs is convolution, primarily two-dimensional convolution. So you're building essentially the core kernel of that and seeing how fast you can make it. OK, so any questions on that? The assignment document has more information, and will be out hopefully later tonight. OK, so background reading for next week. So see how far we get today. But we may get to some work on accelerating deep neural networks on FPGAs. It's an interesting area of compute acceleration these days. So these are 3 papers on deep learning acceleration on FPGAs. I'm going to make the due date 2 weeks. So you have a bit longer to read them in case you want to read more than 0, maybe even more than 1. We're going to talk about, actually we're going to talk some about each one of these papers. So maybe I'll just leave it to the lecture to show you what's in these papers. OK, reading for this week. So 2 pretty different things. First one was about good benchmarking, and second is about data center FPGAs. Okay, and let me give you a course concept map because you might be trying to figure out like how does all this stuff fit together. So what we just finished, I kind of just finished off lecture 4 a bit late, which was how do FPGAs compare to other devices. And what we're doing in lecture 5, which will probably bleed into next week a bit too, is how do we use FPGAs in deep learning, or sorry, in data centers, because it's an interesting application area, and how do we use them for deep learning. So just kind of diving into 2 application areas which make use of some of these programming models. So they're also kind of case studies of what programming models did they choose to use in these accelerators, or what kind of compute models. So hopefully that helps. Okay, so this one's kind of an aside. It's just like how to do comparisons well. So GPUs versus CPUs. How many people read this paper? Okay, so a few people. Any thoughts on it? Loved it, hated it, thought there was major flaws, learned my master's research was totally wrong, I need to go back and change my result tables. What do you think? Any thoughts?
Like that it went even one more layer deeper that just having, say, it, I mean, it tried to go into the trade-offs of the application properties itself, whether like the memory accesses that are required are regular, irregular, if that's being scattering or not, and then how does it map to, you know, a processor versus a GPU and the availability, the depth of caches in one versus the breadth of caches in another. So I think it was quite detailed in that sense.
Yeah, I like this paper too for the same reason, that they really did a very careful job. Okay, it's by Intel, which is obviously bigger in the CPU market than GPU. They're in GPUs now too. So it's a question that has come up before with prior classes is, are they biased? Do they just have an axe to grind? What do you think? Anybody think they did a fair? You can never do a completely fair comparison, right? Like you have limited time, so there's always, you can't have a paper where you say, I absolutely for sure have no error bars on anything. So I'm not asking that. Do you think they tried to do a pretty fair comparison? Or do you think it was like management decided the CPU's got to be shown in a better light, you must write a paper to do that? What do you think? There's those 2 extremes. What do you think?
I won't choose a side, but it was interesting that they had, you know, the 7 kernels that they programmed differently for GPUs and CPUs, right?
Yeah.
So it seemed a little bit like if you write your instructions in a very specific way for CPUs, they're actually not as terrible as we all think. And then my question that I had was, how likely are people to write? I mean, were there a lot of changes they needed to do from what would be found sort of in the wild to get the CPU to perform 4 times worse than the GPU rather than 25 times worse?
Yeah. Yeah, so I think that's a great point. So clearly Intel set out to, some of the Intel researchers who wrote this paper, I think they're probably trying to figure out the answer of are GPUs that much better than CPUs that these various other publications have claimed. And their, spoiler, their answer is no, they're not as much better. They are better on some of these applications, or most of these applications, but not as much better as people have said, when you code for the CPU carefully. And I think it's a valid conclusion, because I've seen this in the FPGA world a lot. People publish lots of papers about them accelerating the following on an FPGA, and they will spend a lot of time optimizing. And the CPU is like I wrote the CPU code at the end and compiled it. And it's not really fair, right? Because it's not an equal effort comparison. So they went in and they really optimized the CPU code in a few detailed ways we'll talk about. So in that sense, it's definitely fair. I actually agree with their comment, though, that the way they had to code some of the CPU, like the CPU code, they would go in and, for example, use the SIMD units that are in Intel CPUs by putting in essentially inline assembly. They're called compiler intrinsics, but they're essentially almost assembly instructions in your C code. So that's very time consuming. It's doable, but it's hard. And I would argue that it's often harder than actually programming a GPU, where the GPU, you're programming at a definitely lower level of detail than you program most CPUs. But once you start putting in this kind of inline SIMD assembly, it actually is usually harder to do that than to write the GPU code. So don't really have an extreme point there. I guess they've correctly identified. Lots of people don't really try to exploit the CPU very well, but they exploit it with such a high level of effort that in many cases I think it's more effort now than it would have been to have coded the GPU version, which I think is what you're getting at too. I think it's a valid point. So, okay, so this is kind of their key result page. They take a bunch of different compute kernels. So this is like a single precision matrix multiply. This I think stands for Monte Carlo, so random number simulations, and you're tracing something. Convolution, which we just looked at, FFT. Let's see, Saxby I think is matrix vector multiply, and so on. Okay, so I'm not going to go through all of them, but a bunch of important compute kernels like linear algebra, convolution, etc. And they looked at what performance did they get after they optimized these programs for the CPU versus what was claimed in the paper that originally claimed a big GPU speed up. And they found that usually the GPU was still faster, as much as 15 times faster, but the average was like 2.5x. And there were a couple cases anyway where it was actually slower than the CPU. And these papers the papers from which they took these applications typically claimed 100x speed up. So 2.5x is still pretty good, but it's a lot different than 100x. So what happened? So I took this table from the paper. It's not super visible, I'm sorry. So they're comparing on a particular Intel processor and a GPU of basically the same vintage, right? So it's important when you compare compute devices that you try to get them from a same era or same process technology, so that it's kind of a metric of what can you do with this kind of device on this process technology, not what can I do with a 10-year-old CPU versus a GPU that I just bought for $10,000. So these are the same vintage. The processor had 4 cores. The GPU had 30 streaming multiprocessors, so the GPU has more cores. That's still true today. Frequency, the processor is a little over 3 gigahertz. GPU is 1.3. That's still pretty similar today. The GPU is actually a bit bigger in terms of transistor count. It's like twice as big. The GPU had about, nearly 5 times the DDR bandwidth. And this is still true. Like, this hasn't changed much. GPUs throw a lot of IOs at building really wide memory buses, and they use this graphics DDR that has tighter specs, is a bit more expensive, and they basically make their circuit boards have tighter specs, etc. Like, the underlying DRAM technology is not really different, but they basically push the buses wider and give less flexibility to the board designer, etc., in order to get much higher bandwidths. So they get a higher bandwidth of DRAM. Both these support SIMD. So the CPU supported 4-way SIMD, the GPU 8-way. Both of those is widened. We talked about that last week. The SIMDs just keep getting wider. So CPUs are now 8x to 16x, and GPUs are up to like 32x. Let's see. When they calculate the peak single precision floating point operations, there is a difference of about 6x. Actually, I don't know how I got 6x. That's about 5x. So the GPU does have higher floating point performance than the CPU. But once they include the fact that the CPU has multiple cores and it has SIMD, the gap isn't nearly as wide as if you just wrote some very simple C code that ran on one core using scalar instructions. Let's see. And so I guess their key point, first key point, which is probably the biggest point they have, is that if you use the SIMD on the CPU, the peak performance of your floating point and basically everything else is much closer to the GPU. It's like 4x closer to the GPU than if you would neglect it. And compilers historically have been pretty bad at using vector or SIMD instructions. They're gradually getting better, but they've usually been pretty bad at using them on CPUs. So you had to code them by hand. So they went in and coded them by hand, and that helped them essentially really improve the floating point throughput of the CPU. The other thing that they did is they went in and they coded to exploit the CPU's features. So they used blocking. Does anybody know what blocking means? I'm not going to go into it in great detail, but okay, let's say I'm doing like some matrix operation. Okay, maybe it's a matrix operation. Well, let's say I'm multiplying two matrices. The very first benchmark they had was matrix-matrix multiplication. A foolish way to do this would just be to write a triple nested loop. I can do this by writing 3 for loops straight out of a linear algebra textbook. But the problem is it's going to go through this matrix n times. It's going to go through it over and over again. And this is a big matrix. I'm never going to get anything out of the cache. I'm just going to always be going to main memory. And the GPU has better main memory bandwidth. So it's going to win. So the right way to write this on a CPU is you don't go through the whole matrix. You do what's called blocking. Blocking means you take a piece of this matrix and you multiply it by a piece of this other matrix. You complete all of those operations, and then you'll take this same block and you'll multiply it by a new block of the other matrix. And your triple nested loop is just going through this, okay? That will now actually hit in the cache over and over again. You'll have this piece in there, and when you go into this next block, it'll still be in there. It's trickier code, but it works much better. And it's a very standard technique on CPUs. So they did that. They used SIMD instructions. Again, they had to do that with quite a bit of effort, writing it themselves. They parallelized across the cores. So in some cases, these papers hadn't bothered really parallelizing across the cores. And that's not that hard for these applications. So they should do that. And then for some of the applications, they could use clever code. So GPUs are not that good at branching. So you try to use very simple code. It's much like what you do in an FPGA. Do things in a pretty repetitive way. On a CPU, they are good at branching. So sometimes there's a more clever algorithm that has more if statements in it, and they could just switch to that algorithm. It's not as friendly to the GPU. The GPU struggled with a few things. So do people know what hardware gather scatter means? So GPU didn't have hardware gather scatter, this GPU anyway. I don't think modern ones do either. It basically means if I need to get my data from various points in main memory, so I need to get these data items, and they're all over the place in main memory. If you have hardware gather scatter, it's basically got a little hardware engine that can actually be told where all my data is in some efficient way, and it can go get it for you, okay? And align it together and bring it on chip, and you can work with it. And then when it goes to put it back in main memory, it basically takes it apart again, does a scatter. Okay, so the GPU didn't have that, so you need a whole bunch of instructions to get the right data in, put it all together into SIMD blocks, basically, where you can now take your multiple floating point units and work with it. So that slowed it down. And GPUs aren't very good with branching. So they can obviously execute branches, but it makes their SIMD units relatively ineffective, right? Most of them go idle, and they're not as good at predicting what's going to happen with a branch. It tends to make a lot of the processor stall, okay? So they don't like branches very much. Which that again just goes back to this clever code. So they're not going to like using clever code. They're going to try to use a more brute force algorithm. Okay, so anyway, that's how they got all of this. The SIMD instructions is getting better. So I have noticed in the last few years that compilers for CPUs are getting better at using the SIMD instructions, whereas they used to not be very good. So this might not be as hard to get nowadays. Okay, so what's the relevance to FPGA comparisons? Yeah, go ahead.
So what's the difference between an SIMD and
Oh, that's just basically single precision versus double precision. So like what they really do is they build a 128-bit wide data path, and they have four, for example, for the CPU, they'll have 4 floating point units connected to that data path. That data path is also wide enough to feed 2 double precision floating point units. So they build 2 double precision units and can do 2-way SIMD. GPUs typically don't care as much about double precision floating point because it's not used much or at all in graphics. So even though the GPU has a data path that's wide enough that it could build, if it built 4 double precision floating point units, it could actually keep them busy. they don't bother. Double precision floating point units are relatively big, so this GPU only built one of them, okay? So that means if you're doing a calculation that requires pretty high precision, the GPU loses a lot of performance. It's really just not optimized for that. That matters sometimes when you're doing really big matrix calculations, for example. So for some scientific calculations, single precision floating point isn't good enough, but you don't see that problem until you get into really big matrices, and now you have to use double precision. So, and GPUs usually, well, they are not as good at double precision as they are at single precision. Does that make sense? Okay, so I guess I've already talked about this. So when you're doing comparisons for FPGAs, people fall into the exact same trap of, I got a hand-tuned, beautifully coded FPGA implementation, and I'm going to compare it to a C implementation that I wrote really quickly. They had 14 benchmarks. 3 of them were memory bandwidth bound. Okay, and they knew they were memory bandwidth bound. Like, these are known applications that use a lot of memory bandwidth. And 2 of them actually had performance that was close to the memory bandwidth ratio of the hardware, right? The GPU versus the CPU. One of them didn't, and it's because that one could use the CPU cache well, so it did better than you'd predict. Okay, 5 of them are compute bound, and those ones actually were also predictable from the appropriate compute ratio. So if they're a floating point, single precision, if you actually looked at the peak floating point of the GPU versus CPU, it was a pretty good approximation of what you were going to get on these 2 devices. And 7 of the 14 were harder to predict. Like, it was harder to say what was limiting them. So why is this relevant? So last week we looked at a paper that did peak computations. It looked at compute density and memory bandwidth. And there was some good questions from the class of like, well, what do you do with this? Does this mean anything? So on these 14 benchmarks, basically 7 of them their performance was predictable from peak numbers. Now the other 7 weren't. So it does say that paying attention to peak numbers is useful if you know the characteristics of your application, but it's not everything. Okay. I think I'm going to take a break there. Any questions on any of that? Okay, and then we're going to move on to data center FPGAs and the second reading. So why don't we take a 10-minute break? We'll come back at 5:26. Hi.
So just a quick thing.
Sure, I was going to check my battery life, actually. One quick. Okay, so the Catapult project at Microsoft was started as an effort to accelerate the Bing search engine. So it kind of grew beyond that. But so who here has used Bing? So it's got a second leading market share in search compared to Google, but Google has the biggest market share. Okay, so Bing still gets a lot of traffic though. So it's Microsoft's search engine. It's a complicated algorithm, and it's deployed across, well, at least thousands, potentially tens of thousands of servers. But it's pretty clear from their paper that it's deployed across at least thousands to keep up with the load. And it's a rapidly changing algorithm. So they want to reduce the cost of computers, power consumption, but they don't want to increase search latency. So low search latency is considered like a key performance metric to keep your users happy. And they also often combine kind of have a pipeline of operations. So even if you have a search latency that's below what a human would detect, sometimes they're combining that search with potentially other searches and putting the data together. So they want each individual search to be pretty fast. They need a very scalable and reliable system. So Microsoft's pretty interesting in that they weren't interested in, I want to accelerate this something with 2 FPGAs off in the corner or even 16 FPGAs stuck in a server somewhere. If they can't do it with thousands of servers or tens of thousands, it's not interesting to them because they can't do it at scale. So they need it to be a data center class system. It's got to be scalable. So they looked at FPGAs to speed up this algorithm at scale. Why did they do that? So they started doing this, a little before 2014 and published about it in 2014 and again in 2016. And the reason that they started looking at FPGAs is concerns that Moore's Law wasn't giving enough performance and not enough power gains anymore. So for a long time, they would just wait for the next CPU generation. Like building accelerators wasn't super useful because at least for them, because by the time the accelerator was out, ready to be deployed at data center scale, they could just buy the next CPU generation, which was twice as good, and it was really hard to keep up with that pace. But Moore's Law has slowed down in terms of what gains it gives us, particularly in power, both performance and in power gains. So that's made everybody, including Microsoft, much more interested in looking at accelerators. So some of these slides I took from Andrew Putnam, who's a senior engineer at Microsoft. It's just like, what is a data center like? So massive scale, hundreds of thousands of servers. And that's like in one data center. So Microsoft is, I believe, the second largest data center provider in the world. Amazon's the biggest. So they have multiple data center with hundreds of thousands of servers. So power is an important quantity. Space is scarce. They're mostly unmanned. So servers fail inside them, and they generally don't send anyone in to repair them. They're just kind of at the data center control layer. It's just marked as this server is no longer good. Don't send it any jobs, and they'll just leave it there until the next upgrade cycle in 3 years, when they'll just go in and rip out big chunks of machines, and that one will come out with those machines. I mean, Andrew told me these are like remarkably hostile, human hostile environments. They're so hot that if they actually have to send someone in to do maintenance, and I can't say this is all the data centers, but he said at least some of them, they actually send them in with like fireman suits, right? Like they put on like protective gear to go in because it's so hot. So they're not intended for people to hang around. So individual servers fail all the time, right? They don't want them to fail, but they accept they're unreliable components. But the overall reliability goal you can see is basically the data center never goes down. So it's got to route around any problems with individual servers. You can't have a single point of failure. So what do their servers look like? So this is the Microsoft Open Compute Server. So they kind of defined their own internal standard. And they're really dense. So they're 1 unit high, which is like that. And they're only half a unit wide, which means they can stick 2 of them side by side in a rack. There's enough space in this for a relatively small PCIe card, but not a huge one. So half height, half width. They could squeeze a single kind of mid-range FPGA in there. They're not interested in buying the biggest, most powerful FPGAs because they're going to buy a lot of these. So they don't want to buy the most expensive chip. They want to kind of hit the sweet spot. And in this form factor, they couldn't fit or power a GPU. So a GPU is a problem just physically, fitting it in even. Their quality metric is performance per watt per dollar. So they care about, obviously, performance, because the less performance they have, the more servers they need. So, but power is a big part of the cost of this. The number that he gave was about 30% of the total lifetime cost of the data center is power. But they also care about how much the hardware costs, because a lot of the remaining 70% is the constant hardware upgrades. So they don't want any, there's little or no maintenance, no accessibility, so you can't have anything that requires people physically going in there. So this JTAG cable is just kind of a pet peeve of his, that a lot of FPGA debugging wants you to hook up a cable, and he's like, you can't physically go in and hook up a cable, don't do that. The machines last 3 years, and they have an upgrade cycle of every 6 months they buy more machines. For the first 18 months, the machines are kind of premium machines. They get things like Bing Search, which are some of their premier services. And then after 18 months, they're a bit longer and they're not quite as new and shiny. They run some of the lower end services that don't need quite as much responsiveness. And somewhere around 3 years, they're far enough behind the curve that they're not worth powering anymore, and they just take them out. Now, Moore's Law is slowing down. So he told this to me several years ago, so it's possible instead of 3 years is now 4, but that's the basic picture. Homogeneity is highly desirable for Microsoft. So they really want to have a data center where they can just farm jobs out here, there, and everywhere. They don't like having, here's my unique compute cluster, or even here are 100 of my unique compute clusters, because they're harder to manage, they don't scale up and down as well, etc. So their paradox is that they would like their data center to be as homogeneous as possible, have all the same kind of compute resources. But at the same time, to get more than Moore's Law can give them, they need to specialize the hardware to certain key applications. So that's pretty hard. So what they did, some of the other things that I visited Microsoft a few years ago, and a few other interesting things they told me are some of the, I don't actually play Xbox, but the Xbox Live kind of system that keeps track of who's winning, the high scores, etc. They said, for example, that produces huge spikes in data center application load. A new game comes out, it's a hot game, people want to download it, they want to be on the leaderboard, etc. So it'll go from like 0 traffic to a reasonable, thousands or tens of thousands of servers are now running that game and its back end and its leaderboard. And then 6 weeks later, it may have dropped down to not much. So they said, you can see the challenge of trying to make, for some of these applications, of trying to make anything like an ASIC, right? There's like no way you can go build a hardware accelerator for that unless it's programmable. So your menu is like CPUs, GPUs, and FPGAs. Like they're not going to try to build an ASIC to keep up with that kind of product cycle. Not everything rises or falls that fast, but they were telling me this as an example of just how varied the workload is and how much it can change over a relatively short period of time. So you can't be saying, I'm going to swap out the hardware to deal with that because you'll always be behind. Okay, so for their data center friendly FPGAs, they wanted to fit into existing servers. They want low power, so they want all the power for at least the generations that I know about, drawn from PCI Express, which limits them to about 25 watts. And they don't want the cost to be that high. So they want, as I said, they don't want the biggest FPGA. They kind of want the one that gives the most performance per dollar, which is usually about the mid-range. Okay, so the first system they built to do this was called Catapult. Well, it was called Catapult, but it turned out to be version 1. And it's a small FPGA card. So you can see here, this is the FPGA card. It fits into that pretty space-constrained server as just a PCIe card. They don't have to take out any CPUs from either a space or cooling or a power perspective, so they can still have 2 CPUs. And CPUs are the workhorse. Definitely for Microsoft, they were the workhorse. I've heard the same thing from Google. I have a friend who works in Google's data center group, and he said, yeah, we buy a lot of GPUs, but compared to CPUs, it's not much, right? Like they love CPUs. So data centers have huge numbers of CPUs. So that was a big deal. They don't want to rip CPUs out of the server and go down to 1 to accommodate an accelerator watt. And for this Catapult V1, what they did is they took a half rack unit and they put 48 that's got 48 servers in it, and they put 48 FPGA cards in them, and they connected the backs of the FPGAs in a torus topology. So this is kind of the wiring diagram here, and this is what the topology looks like with wraparound connections. Okay, so a torus is like a mesh, but you connect the edges to each other. And each of those FPGAs has a fairly fast serial link. So each of those cables is a 20 gigabit per second bidirectional serial link using their own lightweight protocol. So that's one of the nice things you can do with FPGAs. You can just make your own I/O protocol, and they made one that had lower latency. Okay, so this is going into a data center. They can't have like somebody just puts like a bad bit stream in the FPGA and it starts taking out parts of the data centers. Like starts writing things into the routers that connect all the machines, for example, and just corrupts the data center. So what they did is they designed a shell that basically provides it's a wrapper that gives you all the I/Os. So it goes between the actual physical I/Os, so the DDR cores and so on, the PCI Express cores. So that's a mix of hard logic and soft logic that gets you at all these I/Os. Along with like some housekeeping, some housekeeping stuff. So like temperature sensors, and they didn't really write it on here, but they have like a little thing that's monitoring is the FPGA seem okay, and they have these serial links to the other 4 FPGAs that are my neighbor in the torus. So they don't want individual application developers, like somebody who's trying to accelerate part of Bing, to be worrying about, well, how do I talk to DDR again? How do I talk to PCI Express? And they also don't want them just doing something totally wrong and bringing down parts of the data center. So this shell is pre-designed by basically their hardware team, pre-placed and routed, locked down, so that its timing is all closed. A lot of your difficult timing closure often comes near the I/Os because you've got a lot of high-speed signaling going on. So they kind of handle all that, lock it down, and then in the rest of the chip, the bulk of it, application designers put their design in. So they've got a floor plan reason you can go in. And they called this the role. And this terminology Microsoft created has become pretty standard since then. So it seems pretty. Now a lot of companies have done this. They're the first one that I know of that did it. It worked so well that everybody else decided this seems like a pretty good idea. That's probably how we should do it. So what did they do for Bing search? So they actually use 7 FPGAs to hardware accelerate much of the Bing search algorithm. There are still pieces in software. And this algorithm, they won't reveal all the details of it. So in their papers on this, they talk about the algorithm to some level of detail, but it's considered part of the secret sauce, so they don't tell you everything. Basically, they extract what they call features. So you typed in certain keywords, and they go look through for all these documents. Do they include those keywords or not? Are the keywords close together, et cetera? So they get a whole bunch of these features, and they do that in a few phases, and then they eventually turn that into some kind of score with some machine learning algorithm that they won't disclose. The overall algorithm is big enough, it won't fit on one FPGA, so they basically made a spatial pipeline that spans multiple FPGAs. So a bunch of processing happens in the first FPGA, and then it just sends over one of those serial links its results to the next one, and so on. So it is a spatial pipeline that goes beyond the boundaries of one chip. They actually only need 7 FPGAs, so they don't need 48 to do this. So the torus can be configured as a bunch of rings. So they just use the horizontal links to basically make rings of 8. And one of those 8 is a spare. And they can actually, if there's a problem with one of these FPGAs, they can basically shift all the bit streams over one. And as long as this FPGA is not so broken that it can still accommodate a bit stream that just says copy your inputs to your outputs, they basically have redundancy. They can skip over a broken FPGA as long as they don't have 2 broken in one of the rings. Now they use all the FPGAs in one of those 48 racks of 48. It's just they use them in groups of 8 rather than as a single group of 48. And they use some different compute models. So these, what they call free-form expressions. I can't tell you exactly what that means, except they're extracting these Are these words near each other in the document and so on? They basically made a hand-designed data path that could handle all sorts of these expressions and then controlled it with a finite state machine. And eventually they changed that to controlling it with an instruction stream. So the Bing search engine apparently changes a lot. So they not only need this to be fast, they need to be able to update it pretty quickly. So they use some programming styles where they would make custom data paths that are pretty complicated, pretty handcrafted, but then control them with either finite state machines or later on with instruction streams to maintain productivity. Okay, so what did they get? They got a 95% improvement in throughput, so almost twice as much throughput at the same latency. And this is the way they think. Their budgets are all about, I have a certain latency target, how many queries can I send into my servers before they start, some of them responses exceed my latency target. Because if that's happening, I gotta back off, right? I need more servers. The second generation I'm going to talk about in a minute improved that further to 125% throughput improvement. And basically the improvement came from moving more stuff to hardware. So they were still limited by software. They got big speed ups in what they moved to hardware, but there's still stuff in the software. So as they move more to the hardware, it gets faster and faster. The power increase per server was less than 10%. So they considered this a big win in throughput per watt. And so based on this, so it's kind of interesting the scale of things. So Microsoft's prototype system was over 1,000 servers. That was just like the prototype to just proof of concept. It scaled well, it worked well. Based on this, they decided, okay, that's it. We're putting this in a whole pile of servers. The Bing part of our cloud will use FPGAs. So they went to tens of thousands. So the scale at which they work is interesting. Any other thoughts or comments on this? I know Andrew said there's something interesting on this, that when they sent in the papers on this, which is a pretty cool paper, they got some reviewers who said, yeah, it's only twice as fast. I mean, I was hoping for more like at least 10x or maybe even 100x. And he said that was interesting. He thought that was the difference between academia and industry. Because in industry, on these highly tuned super systems that are costing a lot of money to deploy, a 2x gain is really big. And it's really hard to get because you have such a big system. So for example, here they were still limited by software. So yeah, he found that perspective different because he thinks academics probably work on smaller problems and potentially don't bother tuning the CPU code. So they get those 10x or 100x. But he said they were really happy to get 2x. So, and I guess this reviewer comment annoyed him because he still remembered it years later. So. Okay, so that was Catapult 1. And I guess a key thing, maybe a last key thing to notice here is, so the FPGA is kind of a slave to the CPU. Okay, so the CPU talks to the FPGA over PCI Express, sends it data. That FPGA can talk to 47 other FPGAs using this Taurus interconnect. Okay, but the CPU is still in charge. So in Catapult 2, they changed that. Okay, so this is a picture of Microsoft's data center at a very high level of abstraction. So they've got racks of machines. And on top of every rack of machines, they have this top of rack switch. Okay, so that's connecting 96 of these servers together through a whole bunch of Ethernet ports, right? And then to connect those various racks together, they have L1 switches. And those will connect a local part of the data center together, I don't know, some fraction of a row or 2 rows or 3 rows of the data center. And then those L1 switches connect to L2 switches. So you have to go all the way across the data center. You go through 3 levels of switching. If you just have to go to a server that's in the same rack as you go through 1 level of switching. So they have a hierarchical network. And this network's expensive. This is another big part of data center cost. It's not just about putting lots of compute nodes in. You have to put a lot of networking in so that all the data can get to where it needs to go. So what they did for Catapult 2 is, let's see, I think I have this on the next slide. But basically, they flipped the way the FPGA connect to the network. Instead of the CPU connecting to the network and then sending data to the FPGA over PCIe, the FPGA actually connects to the network. So it is the network port. And then it can send data over a little local NIC card to the other CPU. or it can send it to the CPU right beside it over PCI Express. But basically now the FPGA is in charge. It's what connects to the network, and for the CPU to get data, it's got to go through the FPGA. So what that does is this diagram, the intent is to show that they've got kind of two planes of compute now. They have all of the CPUs down here, and they can communicate by going through the FPGA and then into the network. And the FPGAs can directly communicate with each other as well as with the CPUs. So, I'll show you a few slides of why they think this is a superior organization. And it does seem like a superior organization. And they wanted to target different things. So they want to offload the CPU with things like Bing, where the CPU does a bunch of the processing, but they want the FPGA to do some of the more data parallel parts. They have other applications like machine learning, where they want the FPGAs to collaborate with each other. You're going to see this in another paper that we'll talk about either late today or next week. But basically, they can take machine learning models and spread them across multiple FPGAs. So they'd like the FPGAs to be able to directly talk to each other. And then the last thing, which turns out to maybe be the most important of all, is bump in the wire processing. So what that means is all of the traffic to the network is going through the FPGA, so it can process it on the way in or out. So it can, for example, encrypt all of the data going in or out of the network. And that's important because a portion of Microsoft's data center, okay, so Bing is like part of their service data center where people just go and use it. They don't know they're using it, Microsoft runs it. Another part of their data center is Azure, where they sell it to corporate clients. So instead of setting up lots of computers, you talk to Microsoft and you buy some capacity on Azure. And Azure is very popular. So it's between Azure and Amazon. Amazon's number one, Azure is number two, and Azure has been gradually creeping up. And a part of the Azure cloud, where you can rent it as a corporate client, is Secure Azure. So Secure Azure is all encrypted. Okay, so your data doesn't leave the server without being encrypted, not even inside the data center. So it goes over the network, it's encrypted first. Comes into the server, now you decrypt it, process it locally. But before it's going to storage and so on, it's always encrypted. So obviously that improves security, but it also takes a lot of compute. All this network traffic is now being encrypted. So the FPGA being on the network, and encryption is a very repetitive calculation. This matches really well what an FPGA is good at. Another thing the FPGA can do on data going in and out is on-the-fly compression and decompression. So if you compress all the data going over the network, and you can do that fast enough, you multiply your network bandwidth, which is expensive. But you don't really want to use your CPU to do that because your CPUs are also expensive and it takes up a lot of your CPU. But this is, again, a repetitive data parallel streaming application that's can be done very well on FPGAs. Does that make sense? So when I visited Microsoft, I was talking to one of the people from the Azure Secure part, and it was interesting. So they said that like that part of their data center is like physically secure. Like it's in cages with guards outside and so on. They have sub-encryption keys that I guess go on the individual machines, but they're generated with a master encryption key. So that master encryption key would let you decrypt everything. It's like a hierarchy of encryption. So he said when the company wants to change that master encryption key, they have to send multiple people to Microsoft physically in different cars with parts of the key, and then go into the locked room where they will like combine it and store it, and then they'll leave again. So it's kind of interesting. It's kind of like a little bit Mission Impossible. So, okay, so what did they achieve with this? So they got rid of the torus routing, okay? And instead of the torus routing, the FPGAs are directly connected to the network. Okay, so they're like now, well, they're always in the network. If they want to talk to each other, they do it. If the CPU wants to talk something, it has to go through the FPGA. The reason they got rid of the torus routing, well, there are a bunch. So one is kind of shown by this graph. So this graph is showing what latency they achieved in the dotted line. Okay, so latency matters because if they're splitting up a computation where there's some back and forth traffic, they want low latency. So this is the round trip latency in microseconds. And with this 6x8 torus, they can reach up to 48 FPGAs through the torus, and some of them are nearest neighbors, so they get a really low latency. Some have to go through a couple hops or up to, I guess, about 15 hops to get all the way across the torus. So they get up to from anywhere from like maybe 2.5 to 10 microseconds of latency with this torus. And after that, they can't communicate except by talking to the CPU, having the CPU put on the network, so a lot more latency and some CPU load. When they switch to the FPGAs directly talking to the network, they basically, it's a much flatter distribution. If it's in the same rack, so 96 of these FPGAs, they get about 2.5 microseconds. If they have to go to a level 1 switch, it goes up to maybe 7.5. If they have to go all the way across the data center, it's maybe 20. So it's pretty low latency, and it wins for most distances. Like it just goes everywhere, and even for the short distances, it's pretty competitive with this torus. So that's the first reason, just more scalable and pretty good latency. They also said this torus wiring was kind of a nightmare. Like they made custom wiring harnesses so they could hook this thing up, but hooking up like a 6x8 torus turns out to be kind of a pain with this high-speed interconnect. And a really important thing was that they didn't have to teach developers who are making data center scale applications about this new hierarchy of interconnect. So it's hard enough to teach them that, okay, you got to make your compute fast, but you also got to be thinking about how many machines are collaborating, and if they're in an L1 or if they're top of rack switch, like you've got to be watching what you're doing with communication latency. So it's already pretty hard to teach a developer. To teach them, okay, now you're going to use some hardware acceleration, which is already making them really nervous. And there's this new interconnect that is totally different. It's a 48 node torus. It's just like you're trying to drive your developers crazy, right? So this is more regular, more what they're used to. And I guess this is the same thing I just talked about. When you actually get the raw latencies, it's good. Okay, so it still uses shell and roll, but at least in that paper, it actually used the shell, which is just providing the housekeeping, connection to the IOs, et cetera, was pretty big, like 44% of the FPGA. Part of that is because they're using a high-performance networking core that used a lot of soft logic. So in more recent FPGAs, this would probably be better because more of the shell would be hardened. But there's obviously an opportunity here for like FPGA architects to figure out, well, what's in this shell and what's common across different people using this shell and roll paradigm and harden more and more of that, because this is a pretty big tax. Let's see, the FPGAs are now a smart network interface. I already talked about this, how they can do inline compression and decompression. They can talk amongst themselves. They do open themselves up to an important thing, like what if the FPGA goes down? So let's say you program a bad bit stream in, and you don't do it just one FPGA, you release it to all the FPGAs in your data center. Through a process of binary search, by asking different Microsoft people questions, I figured out that at this time they had about 1 million servers. So it's actually, the scale of this is kind of amazing. It's growing 30% a year. So I don't know exactly how many they have now, but presumably well over 1 million. So if you put on a bad bit stream, and they put this FPGA in every single server. So for Catapult V2, they just said it's rolled out across all data centers at Microsoft. So if you put in a bad bit stream and it took down 1 million servers, like this is something the CEO will notice. This is kind of a career decision for the Catapult team. So they were pretty nervous about this. Like, what happens if the FPGA goes down? So for people who read the paper, do you see any mitigation strategies for this? Like, they did do some things to try to make sure that this wouldn't happen. Yeah.
They were keeping like that golden image in Flash.
Yeah, so they put like a safe image of this is a guaranteed working network interface that like if things go completely crazy, if we just reboot the system, it's going to load that in and it's at least going to be a network interface. So yeah, so I think that was a pretty smart one. I mean, you could visualize when a couple of these Microsoft engineers were telling me this, you could see they had thought about this. They had visualized like the late night call about the whole data center worldwide is down. You saw what happened with Rogers when they took out their whole network. Like this kind of thing you'd probably get in the news, but it's not the kind of thing you want to phone up your parents and say, hey, check it out, I'm on the front page of the paper. Okay, so data center prospects for FPGAs. So, I mean, Microsoft is one success story. Of what they've published, so they accelerated the Bing search engine successfully, which is quite a complicated application. We're going to talk about a neural network accelerator they created called Brainwaves. They're also using it to accelerate deep learning, and I know that's continuing because they just hired one of my students to keep working on that. So some aspects of deep learning acceleration are part of what they're doing with this. But probably the killer app that they've had is like the infrastructure part, right? Where it's doing on-the-fly encryption, decompression, et cetera, where it's the coupling of the network and the processing on the fly. And you'll see that Intel and AMD Xilinx talk a lot about infrastructure processing units now, which is really that bump in the wire, like do on-the-fly data processing and things like data centers. So that's probably been more than end applications. That seems like that's been the killer app there. Let's see. So another success story in this domain was a company called Netezza, which is now part of IBM. They bought them. They integrated FPGAs into the I/O path of database searches. So they built a custom disk drive controller using FPGAs. So it did all the conventional things you do in an SSD disk controller, but with an additional feature of you could actually put the first part of the database query, like the first set of filters, right in the disk controller. So the CPU could send it some instructions, and it would basically configure some kind of hardware in the FPGA to actually do the first stages of filtering, essentially right at the solid-state disk controller level, which would cut the amount of data that went back to the CPU by a large fraction. And Netezza said it sped up database searches by 10x, and that's why IBM bought them. And I believe it's stated by Intel that a key reason they bought Altera was actually because of the data center market for FPGAs. So Microsoft is clearly still all in on it. Baidu and Amazon have some FPGAs in their data centers, but not at nearly the scale. So the jury's still out of this is going to be in all of them or some of them or what. You do see a lot of infrastructure processing units advertised now too, of that angle of don't worry about accelerating the end application so much as the infrastructure, which is more under the control of the data center vendor. So it's maybe a bit easier target. Okay, so that's it about Catapult. Any thoughts or questions on that? If you haven't read those, well, how many people read those papers on Catapult, or at least one of them? Okay, that makes me happy. I mean, they did really good papers. There's a lot of, there's a large and very capable team that did a lot of really interesting studies, I think. So, okay, let's talk briefly about ways to connect a CPU and FPGA. So these data centers have this problem. Accelerators in general have this problem. So Catapult 1 connected with PCI Express by 8 Gen 3. So PCI Express has a whole bunch of different generations. They just keep updating the signaling rates, so you get higher and higher speeds. And then the by 8, you can make more parallel lanes. So by 8 just means you got 8 parallel lanes, and Gen 3 means they're all running at 8.5 gigahertz. So that provides 8.5 gigabytes per second. It's a fairly high latency. PCI Express is decent for transfers of large amounts of data, but it's pretty slow if you just want it for the first piece of data. PCI Express is a standard bus, which is nice. And when the FPGA wants to get data from the CPU, wants to get a large amount of data from the CPU, it's going to do a direct memory access. So it's going to read it directly over the PCIe bus from the CPU's memory. That's going to use physical memory addresses. So it means the CPU, which its programs are actually computing using virtual memory, which is mapped. You guys all know these terminologies, I think, right? So that virtual memory is mapped to different physical pages, so different parts of the actual physical memory. You have to do what's called pinning. So in order to send data from a CPU program, which basically physically it's the data of that program might be all over the place in memory. It's in different pages mapped to different parts of the physical memory. The FPGA is told, okay, transfer data from some certain physical address. And in order for that to work, basically the CPU has to take a certain region of memory and do what's called pinning it, like saying, I'm going to keep this memory at these physical addresses. I'm not going to move around those pages because that would screw up my FPGA trying to read from them. And generally it involves a copy too. So the CPU is computing some data, using virtual addresses. They're going to certain pages. Before it tells the FPGA you should copy over this data and do some computation, the CPU has to copy it into this region with known physical addresses that it's going to tell the FPGA about. So there's generally an extra copy when you want to go from software to a hardware device like FPGA, like an FPGA. Does that make sense? This is normally handled for you by the driver. So it may be behind your back, but it's happening. It causes some load on the CPU if there's a lot of memory traffic. So another way that people have proposed and built to hook a CPU up to an FPGA is to use what's called a coherent interconnect. And the first one of those was something called CAPI from IBM, so Coherent Accelerator Processor Interface. And then a recent one is CXL, which Intel uses along with other companies. This one is becoming kind of a standard, okay? So the physical layer is still PCIe. So they use the PCIe signaling levels, use the same IOs, et cetera. But you can now use virtual addresses. You can use virtual addresses because basically the FPGA basically can talk to this special port on the processor and using virtual addresses, okay? And the processor will look up the data in its caches if that's the most recent copy of the data from that virtual address, and otherwise it'll figure out where it is in main memory and send it back to the FPGA. So there's some advantages to this. You don't need to do this copying. You can just ask the CPU for data, and you'll get it from wherever the most recent version is. So caches, main memory, you ask for it in virtual addresses, and there's no extra copies. The idea of this is that if you're looking for little bits of data, this could be lower latency. Because if the data is in the CPU cache, you just get it straight from there. That's faster than main memory. You don't have big copies, et cetera. For big blocks of data, it's probably not so much of a gain. Because if you're going to move a lot of data, the data transfer time probably dominates. You didn't like the extra copy, but you could probably tolerate it. So the idea of these interfaces is generally to allow finer grained cooperation between the accelerator, like the FPGA and the CPU, so that they can kind of be, you can be offloading smaller bits of computation, and then the accelerator can just ask for little bits of data as it needs them and get them relatively quickly from wherever they are in the CPU memory hierarchy. So far these ones, it's not clear though that we need this. Okay, so most of the successful uses of accelerators like FPGAs or GPUs have actually been based on more of a bulk transfer. You send a lot of data over PCIe, and they do a bunch of crunching, and then you get some data back. And my group did some work with CAPI. It's harder to figure out applications where you can get a good speed up, but have this kind of fine-grained cooperation that is enabled by these coherent interfaces. So that's my unsolicited opinion on them. These exist. It's not clear they're getting as much market share. Well, they don't have as much market share as just you put it on PCI Express and do these bulk transfers. And is not clear if they ever will. Like, it's not clear if that's just a matter of time, or maybe there just isn't a need for this. I don't know if anybody is actually doing any work with any of these and has a contrary opinion or not. I know we've got a bunch of people from Intel and AMD here. You go like, I'm on the CXL team and it's going to rule the world. This is your chance to speak up. Okay, so it looks like no CXL advocates. So anyway, so when these first came out, there was some fanfare of maybe this is the future of communication between FPGAs and other accelerators and CPUs. But as I say, it's not clear that we really need them. For FPGAs, at least, I still see many more acceleration cases where people are using traditional PCI Express as the communication medium. All right, so any questions on any of that? Otherwise, it's on to a different topic. Somebody asks a question, you can also give a chance for your classmates to catch their breath. So you could be like a hero to your class, right? You just like ask a totally irrelevant question, right? So I'll let you ponder that. But, Okay, so the next thing I was going to talk about, this is like the last thing we're going to talk about before we kind of switch gears and go deep inside an FPGA and look at how it's architected, is deep learning in FPGAs. Because it's been interesting, it's a very active area of research for acceleration, and it kind of highlights some of the compute models we talked about. So first thing I want to talk about is accelerator styles and some results from those accelerator styles. And I should acknowledge one of my PhD students, Andrew Boutros, who helped making these slides, who's now at Microsoft, who also made some of these slides. Okay, so I'm going to give you a, how many people here are, okay, who has heard of deep learning? Okay, I don't believe there's anybody who has deep learning. So who's not going to put their hand up no matter what I ask? Okay, so I'm just checking. Okay, so most of you heard of deep learning. How many people would consider themselves quite familiar with deep learning? You're like, yeah, I'm writing algorithms and I know what's going on. Okay, it's not too many, so that is fine. Don't worry, you don't need to know that much about deep learning to understand what I'm going to talk about, but ask me if some of the terms are, it's difficult for me to know people's backgrounds. So if you kind of go, I don't know what that term is, just ask. So I'm going to give you a very few preliminaries, but this is very far from a course on deep learning. So it's a very little bit of preliminaries so you can understand some of the acceleration results. Okay, so this is like a marketing kind of slide. So deep learning inference. So there's two phases of deep learning. There's like training, where you try to come up with the weights, which is done once. And then there's inference, where you're actually using those models to make predictions or decide things, and that's done all over the place. FPGAs, I think they're much more likely, well, they're much more interesting in inference than they are in training, because inference happens all over the place, right? So, and FPGAs, as we talked about earlier, they have custom IOs. You can build them to make all sorts of unique systems. So that's an advantage for FPGAs. Also, inference is tolerant of low precision. And that's also favorable to FPGAs, because their hardware gets smaller the lower your precision is. Training is much less tolerant of low precision. So all the acceleration I'm going to talk about is about inference. Where do we do inference? You can use it for finding diseased tissue in an MRI, credit card fraud, figuring out if a bad person is on your doorstep with your smart doorbell, interpreting your speech, automating. Amazon bought a robotics company that was actually founded by a U of T alumnus, and is automating their factories to use, or their warehouses to use those robots as much as they can, and obviously things like driver assistance. So, and this is like a tiny set of what are the applications that deep learning is going into. Most of these systems won't be all deep learning, right? So they'll have custom sensors and outputs and so on, which is again makes them quite interesting for FPGAs. You got a deep learning part, but also pre-processing and custom sensors. Energy, efficiency, and latency matter in many of these applications. I can't say that they probably matter some in every application, but for a lot of them, it's really important. Okay, so let's take the edge. Your edge basically meaning I'm not in a data center. So this is probably the biggest embedded device you're ever going to get, like an electric car. So a Chevy Bolt in a city averages about 6 kilowatts of power draw from its batteries to keep its engine running. This is an NVIDIA AGX Orin card, so a card intended for autonomous driving. Lots of GPUs in it, and it consumes 750 watts. Okay, so those car batteries can definitely power something that takes 750 watts, but it's kind of interesting. This is like the biggest embedded device you're ever going to find, and that's still a significant power draw compared even to the engine. Not as big as the engine, but it's not negligible. So, you care about energy efficiency even here in the car, because you'd like to extend the range. But clearly, if this was going in like a doorbell or something, it's going to have a much lower power budget, so you care even more. The other thing you care about here is latency. Okay, so you don't. So let's take driver assist. So you're getting a whole bunch of video frames, and you're deciding if there's a pedestrian in front of you or not. I'm going to talk about this in a couple of slides. But one of the ways, well, you would like to make that prediction of do I have a pedestrian in front of me or not very quickly. Okay, it's not enough to just be accurate. If that prediction comes 2 seconds later, you've already killed the pedestrian. It's just you have like some signal on your dashboard saying, yes, that was a pedestrian, right? So it's actually pretty important that it figured it out very quickly so it can apply the brakes. And you're going to see this is actually something that is friendly to FPGAs. Okay, so low latency they're good at, and energy efficiency they're good at. Okay, does this only matter in the edge? No, it also matters in the data center. Okay, so here's a picture of, I told you these Microsoft data centers are huge. I mean, they're all huge. This is a picture of a Microsoft data center, and the scale of the thing is kind of just amazing. Like, it just kind of recedes into the background. As I mentioned, the key performance metric is performance per watt per dollar. Power is about 30% of the cost. There are various estimates of how much electricity data centers take, but they're all in the low, like they're all in the non-negligible amount. 2 to 3% today is a common prediction or a common estimate, rising to 6% by 2030. That's not guaranteed that we're going to get to 6%. So certainly companies like Microsoft say, well, we're being clever. You're assuming we're not that clever, so we won't get to 6% because we'll be clever. And that's probably true, but that's where we need to have innovation to avoid just scaling compute and taking 6%. And 6%, you might go, that's not that bad. 3% sounds even better, except like that's the whole world's electricity use, right? So including heating and lighting and so on. So it's a significant amount of power. In the data center, low inference latency is also important. If it gets too high, it affects your end user experience. So I already talked about in Catapult how Microsoft had these targets of a search result has to come back in this amount of time. Microsoft's target for a paper we're going to get to in a few slides was 2 milliseconds inference latency for a convolutional neural network. And the reason, actually no, that was for an RNN. That's really fast. You might go, well, like a human can't detect whether the data center answered in 2 milliseconds or 20 milliseconds, which is true. But basically, Microsoft said they combine their machine learning algorithms and pipelines. So they don't just take one answer and say that back. They take that answer, combine it with 4 other predictions, send that to another model, and they create unique services. If each one of those models is really fast, their deep learning developers can just combine them in services without worrying too much. They can say, I can combine 30 things in series and it's fine. So they like that. So if it was completely impossible to do that, they would just forbid that behavior. But if they can make inference that low latency, then it makes their task of making good applications better, so they'd rather do that. Does it make sense? Okay, so, but for FPGAs, this low power and low latency are kind of, in inference is kind of their strongest suit. Okay, so CNNs. So I already showed you this picture before. This is just a reminder, what does a CNN look like? And the first application example I'm going to show you is a CNN. So CNNs classically were used to do things like classify images. Say what is it? Is it a car or a truck, etc. With a few extra layers, well, maybe 10 extra layers. If you add some extra convolutional layers out here, and then some extra logic, you can do things like object detection. Okay, so you can take this CNN, and instead of classifying an image, it'll actually put boxes around all the pedestrians, for example, and classify them as, well, all the objects, and basically classify them as pedestrian or lamppost or curb, etc. So the core of object detection is actually also a CNN, with a little bit of extra stuff at the end. And yeah, one of the application examples I'm going to show you, does both. It'll do both object detection and classification. Okay, the other kind of application example I'm going to show you is from recurrent neural networks. So recurrent neural networks, so I guess the key thing about convolutional neural networks is you're basically, well, you're convolving. Your key computation is take a local region, do a bunch of multiply adds, produce an output, and slide that around and repeat it. Recurrent neural networks don't do that. Basically, here are your neurons, and this neuron is affected by all of these neurons in its input. Okay, so there are weights from all of them. And the same thing for the output layer. Okay, so this recurrent neural network is fully connected. It doesn't have this sparse pattern that we had in CNNs. And it also has feedback loops. Okay? So recurrent neural networks, and there are other variations on this that I'm not going to talk about, but the other application example is recurrent neural networks and kind of related things. These are good for sequence processing. So turning sounds into text, turning words into meaning, translation, etc. So they tend to be sequence processors because of these feedback loops. Okay? And the core of a CNN is convolution. The core of these networks is matrix vector multiply. You basically have a matrix of weights that represents basically all these edges that is getting multiplied by activations, the state of each of these neurons. And you apply that at every single layer, and that's the core of this. Okay, so convolutional neural networks. This is a slide from Microsoft. And I'm not going to go through all the boxes. The key thing is convolutional neural networks are compute bound. Okay? They do order n to the fourth computation on n cubed data. And in fact, it's even more. This k is the dimension of the filter. So how many taps in your filter in each dimension. So if your filters are big, it's even more compute bound. So for convolutional neural networks, yeah, the main thing is how many compute units can I build? Then I still need to keep them fed. But if I can keep them fed, I'll be limited by computation. For these RNNs, okay, so these are RNNs and various other flavors of RNNs, these recurrent neural networks, they are dominated by matrix vector multiplication, so they're not compute bound. With order n squared data, they also do n squared compute. So both memory and compute matter. And if you can easily become, just spend all your time waiting for memory. Okay, so these two different classes. This is basically about image processing and object detection. This is about text processing and sequence detection. They have different behavior in terms of memory versus compute limitations. Does that make sense? Okay, and I've got 2 more slides on background. So this is like this is the fastest introduction to deep learning you're ever going to get. It's not going to go deep. Okay, so a common thing that people do to improve throughput, like try to get more throughput from the same hardware, is something called batching. So does anybody know what batching means in deep learning? What do you think?
Like cache bound, which is to really process the large amount of data as it maps to the individual units, one batch at a time.
Yeah, it's actually a good analogy. So I'll just repeat that in case people couldn't hear it. You said it's much like blocking for caches to get better efficiency. And you're right, it's the same idea. So what batching is for, it's basically when I've got this big weight matrix. So let's take the recurrent neural networks because it's more obvious here. I've got this big weight matrix. And again, this weight matrix is encoding essentially all these edges, right? If I add up how many edges here, if I have n input neurons and I have n output neurons, I'll have n squared edges between them in this style of neural network because it's fully connected. I got all the edges. So I have a weight matrix that says how strong each of those edges or weights are, and it's n by n, so n squared storage. And I basically bring in one input. I multiply this matrix by that input. It produces the output layer. And then I basically go process that output layer. I basically bring in another matrix of weights, and I take that output layer, which is now a bunch of activations, and I multiply this new matrix times that vector. So I'm going to be dominated by bringing this matrix in or various matrices in over and over again. So what batching does is instead of saying I'm going to take one input, let's say it was one image, I'm not going to send one image through my neural network. I'm going to wait until I have several images. Maybe it's a video stream. So I get 30 frames of video, and then I'm going to send all of those images in basically one after another. And I'm going to bring in this weight matrix, which again represents this first layer here. And I'm not going to do one matrix vector multiplication. I'm going to multiply this matrix times all 30 of those inputs. And I'm going to produce 30 partial outputs. And then after I've done that, I'll bring in the next weight matrix that represents these edges, and I'm going to multiply that weight matrix times all 30 of my partial outputs. So what that does is it lets me amortize how often I have to bring in these big weight matrices, and that amortizes how much memory bandwidth I need. And I will get more throughput. But it's also bad for latency, because I have to wait for, let's take the video example. I wait for 30 frames of video, and then I send them all through, and then they're all going to come out at the same time. So in some cases, that's fine. Okay, let's say they're not 30 frames of video. Let's say they're 30 images from around the web. And let's say Google is classifying them in its data center so that when you do Google image search, you find enough cats, right? And enough cars and so on. That's fine. Batching that up is fine. All Google cares about is that they actually go tag every picture on, Instagram once a day or something, right? They don't care too much about exactly what the latency was of all those images. But if this is a video feed in that car, then it actually is a big deal to batch it, because you get 30 video frames and then you analyze them all together. So now, I don't know, half a second or a second later, you're told the last 30 frames of video actually had a pedestrian in them. You would have much rather have been told, 1 second earlier, I think there's a pedestrian, rather than be told 30 times there's a pedestrian, but later. Does that make sense? So yeah, batching is a technique. As you increase the batch size, you can tend to use your hardware better, because you're amortizing your memory traffic. But what it does is, as you increase the batch size, your latency is going up. Partly because you're just waiting for more inputs, but also because you're sending them all through together. And so they all have to be computed together. They get in each other's way, basically. Does that make sense? So this is a slide from Microsoft, because Microsoft makes lots of nice slides. These dots are basically, they're saying this is where we'd like to be. Okay, so in their accelerator that they built in one of the papers I'm going to cover, their target is to get good hardware utilization, but without big batch sizes. And therefore, they would also get low latency. Does that make sense? And they were successful in doing that. So this is an example where that trade-off actually suits FPGAs pretty well if you're able to develop your hardware in the appropriate way. Does that make sense? Does everybody kind of grasp what I mean by batching? Okay, cool. Okay, so got a few minutes left. We'll just kind of go through part of this, but not all. So let's talk about accelerator styles on FPGAs for deep learning. Yeah, and I want to acknowledge again my student Andrew Boutros, who made this beautiful set of next few slides, more nicely formatted than mine. On this axis, we've got efficiency, and this axis, generality. So the earliest accelerators on FPGAs were layer engines. So they basically didn't do the whole neural network. They would take certain layers of the neural network or certain operations. They would accelerate that and leave the rest on the CPU. Okay? Their efficiency wasn't that high because, well, you get a communication bottleneck, right? They're only accelerating part of the network, and also you've got some more communications. So they could get some wins, but there's some limits as to what they could get. Don't worry about the pictures. They're pictures from specific papers. You can look at those in the online slides if you want. But you can consider the pictures just kind of like, decorations. You're not expected to understand all the details in those. The next set of accelerators would be model-specific accelerators. Okay, so that means they've gone further than just accelerating certain layers or certain operations. They took the whole network, accelerating it all. But they did that by essentially handwriting custom hardware. So they built it in the FPGA. It does this one model. And if you want to change the network in a significant way, you need to get somebody to go rewrite a whole pile of that. Okay, so your efficiency is high, but your generality is, it's low. It only does one model, and it's going to be a lot of work to put another one in. And depending on the application you're in, the models could change a lot. So another friend at Google tells me that not the model, but the weights in their search engine learning algorithm, they actually update multiple times per day. Okay, so they don't change the model multiple times per day, meaning the architecture of the neural network, but they change the weights very frequently. And the reason you can actually have like essentially like breaking news, right? Like at first I was very surprised by that, but you could have some news story, I don't know, the latest abomination by Trump, for example, everybody's searching for it, they can't help themselves, and you want your neural network to go find that rather than, you know, some kind of catastrophic behavior he had a year ago. Yeah, so some of these models get updated quite frequently. Now, again, that one is weight updates, which isn't as big a deal as changing the architecture of the network, but in places like Google, they still change the architecture of the network reasonably frequently too. The next style of accelerator is basically they're these model-specific accelerators, but they add in a domain-specific compiler, essentially some kind of customized creation engine, software. So it's like a custom high-level synthesis, right? But highly customized to this domain. So it still makes you hardware that runs this particular network very well, but you didn't have to create it all by hand. You described it to the tool, and the tool knew how to make specific hardware. Now, if you go underneath the hood of a lot of those tools, like the one we will go under, you'll find that it's not magic, like people by hand have made efficient hardware under the hood, but they've put it in a parameterized way so that if you change the network, the tool knows how to like put it all back together again automatically. And then the last style is overlays. Okay, so overlays means it's instruction set programmable. So you build some data processing engine. So it's a form of processor. It's got an instruction stream. But these are typically very highly customized kind of weird soft processors. They're not like the simple soft processors that we talked about earlier. They have been hand-tuned to be good at a certain style of neural network and to have a huge amount of parallelism that is then controlled by an instruction stream. And so this style you can adapt to a new network, you know, relatively quickly because you can just reprogram it with instructions. You don't actually have to change the underlying hardware that's put in the FPGA. That tends to cost you some efficiency, okay, because you are still building, it's a very customized soft processor, but it has still got some of the processor overhead. But its generality is kind of the best because to change it to a new network that's not too different is kind of the fastest of all. Does that make sense? If you want to read more, here are a few references on this, but there are lots. There's lots of work in this area. Okay, so if I take away all the pictures, this is what we're left with, those 4 points. So all of these, well, I guess these are the 2 ones that are really the most successful at this point, I would say, because they have the most automation. They're trying to achieve, you know, good performance despite the fact that FPGAs have this overhead of reconfigurability. So, right, so you've got to specialize. You got to do something that's different than what you'd get in a processor or a GPU, or there's no point, right? So you got to make your hardware somewhat customized to neural processing. And at the same time, FPGAs are harder to program than a GPU or CPU. So what tooling do you put on top of that so that it's not too hard? Because if you just say go write a whole bunch, if you tell a neural network developer you will go learn Verilog and write a huge amount of Verilog, they're probably not going to do that. So you got to put some abstraction layers in. Okay, so I'm not going to go into this today. I'll start on this next week. But we'll take one example from each of these and just show, well, how did they tackle that? What performance did they get? But there are multiple papers in these areas, so you can definitely go find additional examples of both overlays and custom hardware generators in this domain. So we'll go over that next week. And then we'll come back to well, how many people are interested in deep learning acceleration? Let me ask that. So 2, 3, 4, okay. How many people are interested in deep learning acceleration? Okay, so a reasonable number. So my plan is to actually come back to this again towards the end of the course, because there's also a bunch of work on FPGA architecture. Like, so this part is about how do we build accelerators with current FPGAs. There's another vector of research, which is how do we change the underlying hardware to be more efficient for deep learning. So my plan is to come back to that after we've studied a bunch more about FPGA architecture to look at what those are. So that's why I'm asking how many people are in deep learning, because courses are kind of a zero-sum game. Anything I put in, I have to take something out. And whatever I take out, at one point at least, I thought was important. So that's why I ask. I have to think about it. Okay, thanks everybody. I was going to say goodbye to that.